this computer. Okay. So first and foremost, I know that it is Ramadan, and so I do know that there are a number of students who are observing Ramadan. So if the fasting makes taking tomorrow's an exam an issue for you, please email me and we can schedule a time so we can proctor that exam after you've had the chance to eat after your fast in the evening. I'd be happy to proctor your exam online because I know how much how difficult it is to try to do something academic when you're fasting. So if that's an issue, please let me know. Otherwise, I wish you a meaningful and easy fast. So, with that, now with regards to the exam, we will go over the practice exam today. So let's pull that up on Canvas. Okay. Okay. So sorry, announcements, that's where it was. Oh. Okay. So let's start with first questions. So you need to model which patient should be seen next in the hospital. Patients should be seen in as close to the order of arrival, but patients with a more severe condition should be seen first. This is very obviously a priority queue. I've used this as a priority queue multiple times. This is the idea of triage, where basically people with more serious injuries need to be seen first, head trauma and the like. But if you've got a broken finger, you're in the back of the line. Sorry, it sucks, but you know, it's not life-threatening. A router needs to hold packets in a buffer and deal with them in the order they appear, right? So, but routers just take in bits and send out bits, and they have to do so in the order they get them in. That's a queue. You need to model a hierarchy. Anytime a hierarchy is involved, that's a tree. Any kind of hierarchical structure, be it a family tree, a taxonomical tree, you know, an org chart, those are trees. Anywhere where there's something at the top. Now there's sometimes more like flow charty stuff, but that's graphs and we haven't covered that yet. Next, you need a data structure to hold your previous decisions in case you need to backtrack. Yes. Priority queue and queue. Number 4, you need a data structure to hold your previous decisions in case you need to backtrack. That's a stack. An argument could be made for a linked list. And if so, make that argument saying that you can use a linked list as a stack, right? But in general, when you want to backtrack, you want to use a stack. The wrong answer always is recursion, because recursion is not a data structure, it's a technique. Yes.
When would you use like min heap and max heap?
You use min heaps and max heaps to build priority queues.
Oh.
You typically use heaps for priority queues because what you do is you're keeping somebody in the you know, at the front of the line. So answer the following vocabulary questions. The node at the top of the tree is called a root. That should be fairly straightforward. The links from a node to a successor are called what? And there's multiple answers here. We could have gone with what? Branch is correct. Edge is correct. Technically, if you wanted to be a smart aleck, you could put down link, because I just used that word to describe it. As you know, those all make sense. Pointer, I would probably accept. A predecessor of a node in a tree is called a what? Something that comes before it. Yes, the parent. And if you want to be more generic, you can say it is the ancestor, right? The ancestor. And what is our nodes that have the same parent? Siblings, right? Use you can leverage family structure terms as much as you want to over here. So if you say that somebody is the aunt node or uncle node, and I like aunt because it's one syllable and one letter less. So then, if it's the aunt node, then it's your parent sibling, right? Describe without using code how to calculate the height of a tree recursively. Now this one, I think I went over because the student asked it, but that could have been a different class. Probably was this one, but all right. So we've got this. So we want to know, we've got this tree over here. How do we calculate the height of this tree recursively? Where basically the left node and the right node are both things. Well, first off, if we're in this case where we don't have a node, guess what? The height's 0. So otherwise, well, I know my height is 1, right? I know that I have a height. And so my height is 1 plus the height of the bigger child. So that's how you basically calculate it recursively. You figure out, okay, I know how big I am. I'm 1. So it's 1 plus whichever one is bigger, right? You can use. I can probably slow down a bit and stop trying to speed through it so much. So draw an example of each of the following types of binary trees. Use a different example for each possible tree. And I mentioned that because, again, I write these exams to make sure that, because some people like me are smart Alex who will say done, because this is both full, complete, and perfect. So that's why we're going to use a different example for each, because that is not illuminating. That's just a cheap trick. So a full tree is a tree where we have all the nodes have 2 children or no children. Every node in this tree has 2 children or no children. So this is also full, right? Right, because every node has 2 children or no children. If I add a single node over here, but not a node over there, boom. We've got this tree is no longer full, because apparently for trees to be defined as full, you have to have 2 children. Okay, I'm going to skip complete for a second and go down to perfect. Perfect is defined by a formula for binary search trees that are perfect for a given height h. So a tree of height h is perfect if and only if it has 2 to the h minus 1 nodes. That's a very mathematical statement, but what it comes down to is that there's only one way to draw each of those trees, right? If it's height 1, that's the only way it can work. Height 1 to the first power minus 1 is 1. To the second power is 3 nodes, and there's only one way to make a tree with 3 nodes in it. Similarly, 7 with height of 3, that's 7 nodes, and there's only one way to make a binary search tree of a minimum height with this many nodes, right? That's the idea of perfect. You can, I mean, it is possible for me if it's like, I could make this with 3 nodes, but it's not the way to make it with a minimum height. There's only one way to make a perfect tree with the minimum height. Make sense? So, and remember, and if you have trouble remembering that, remember that just perfect trees look like the mathematical examples of trees, right? Every node, basically it's completely symmetrical and completely filled out on the bottom. Okay. Which brings us to the idea of complete trees, which are not. Now, perfect and full can be checked by a recursion, but complete is a lot more difficult, because a complete tree is perfect. A complete tree of height h is perfect through h minus 1 for a height of h minus 1. So that upper part is perfect. But the lower level is filled up like this from left to right. So that's a complete tree. This is also a complete tree. This is a complete tree. This is not a complete tree because it has some gaps over here. Right, so it's perfect on the top layer, and then the bottom layer is filled up with as many nodes as you want, but they have to be filled up from left to right. Make sense? Basically, if we were to store this thing in an array form, like we would for a heap, then there would be no gaps. There'd be no nulls in there'd be no gaps. Make sense? Right, and complete trees are what we want to use for heaps. Okay. Tree operations. Draw the binary tree that forms after inserting the following integers. 42 inserted first. And obviously you want to insert these in order, just not willy-nilly. So what we're going to do is that 42, because that gets inserted first, that becomes the root. So 10 is less than 42. 50 is greater than 42. 12 is less than 42, greater than 10. So 12 goes over here. 17, less than, greater than. 17 goes over here. 80 is greater than 42, greater than 50. Negative 12 is less than 42, less than negative 10. 100 is greater than everything else we put in, so it goes all the way to the right. Now here's the interesting parts where we get 96, that is greater than, less than. Right, 96 is greater than 42, 50, greater than 80, less than 100, so we go to the left. So there's nothing on the left, so we put it there. 105, greater than 100, boom, 5. And 86, it's greater than 42, greater than 50, greater than 80, less than 100, less than 96. So 86 goes over here. And 72 is greater than 42, greater than 50, less than 80. So as you can see, the easiest way, basically with trees, the easiest thing that can happen is just making a careless mistake, right? So be sure to double check your work. Okay. Now we're going to use this. Because I'm lazy, I was lazy for writing this, I would just simply say, hey, using your previous answer, draw what happens when you remove the following: 42, 12, 17, and 96. Right, now when we remove a node from a tree, we have 3 cases. Case number one is that we are removing a leaf node, which is fairly straightforward because guess what? All we have to do to remove the leaf node is just tell its parent that the child is now null. And that's it. No updates need to be made to the tree whatsoever. What if I want to delete this node? Well, if I have one child, that's also easy. Even if that child is the root of a very massive subtree. Right? Even if that child is the root of a tree or massive subtree, deleting that becomes no issue, because all I have to do is just simply say, hey, my parent, please adopt my child. And so what happens to delete that node is you just connect those. And then finally, what if I have 2 children? Okay, if I have 2 children, I have to restructure the tree. Or rather, if I don't want to restructure the tree, I have to find the next in order predecessor, or the next in order successor. I like to do the next in order predecessor, which means the biggest node that's small, the biggest node that is smaller than me becomes the new root. So for instance, if I'm deleting this node, I'm going to grab the biggest node that's smaller than me. So I go 1 to the left and I go all the way to the right. So I grab this node over here, and this node becomes this, then we copy that value over here, and then we delete this node. Because now, and by now that we delete this node over there, this node is always going to be one of those two previous cases. Either it's going to have one child or no child. So how do we solve this? So with this one, 42, to delete 42, that is two children. So we are going to delete all, so what we need to do is we've got to find the next door predecessor. So we go one to the left and we go all the way to the right. One step to the left, as many steps as possible to the right, and we find 17. And we see that 17 is the biggest value that is smaller than 42. So what we do is that we copy 17 over here, and then we delete 17 from this tree, essentially. So you delete this node, and deleting this node is just a matter of just deleting it because it has no children. Okay. 12, also likewise, deleting that one's fairly easy because it's got no children. 17, this one's kind of a trick question because again, you're deleting something with two children. You go one to the left and you go all the way to the right, and all the way to the right, you're still at 10, right? The rule still applies there. So what we're going to do is that we copy this value over, delete the original 10, and deleting the original 10 is just a matter of, well, that's one, it's got one child, so we delete this node and connect it to, and connect the parent to the child. 96, again, that's the case one again, where we delete a node and connect the parent to the child. All right. Which of the following is a pre-order traversal of a binary tree with the subtrees left tree and right tree? So pre-order traversal, post-order traversal, and in-order traversal, you always do the left tree before your left child before you do your right child, no matter what. The question is, where does the root node come into play? That's really the only difference. So pre-order means you do the root node before everything. So that answer is do the root node before everything. So our answer is B over here. Process the root node, then do the left node, then do the right node. Likewise, post order. Do your nodes first, then process the root node. Sorry, do your subtrees first, then process the root node. In post order, the root comes last. I do handle my children's before I handle myself. So, and then in order is what we do when we want things to come out in order, which means do everything smaller than me, then do myself, then do everything bigger than me. So that would be, so in order is A. All right, heaps. Heaps are in many previous semesters before I started emphasizing this point. Heaps was where a lot of students would lose points because they would not know how to do heaps as opposed to trees, and they would draw things that were not complete trees. And so as a result, I would just mark that wrong because a heap has to be shaped like a complete tree. So it gets built differently. Heaps are built differently than everything else. So first thing we do is that, and ignoring the underlying array means that, you know, all heaps are stored in this array, but you don't have to write out the array. You don't have to know the formula. I want to know the heap structure because we can just do a breadth first search of the heap visually of the visual heap and kind of create that array. So it's not needed. So we first put in 8, that becomes the root of the heap. And so this is a min heap, meaning the smallest item is at the top. So a great way to think about min heaps is that the smallest item bubbles up to the top and the heaviest items sink down to the bottom. That's the way I always like to think about it. Max heaps, it's the reverse. Maybe you gotta like think maybe anti-gravity or something, but who knows? But 8, I mean, if you really wanted to act like a min heap, you can always just make a max heap 1 over the numbers in the max heap, and then you got the same rule. But all right, so 8, and now what we need to do is that we always add a node in the next node in the place that would make it complete. So, right, if we have a node here, then it goes here, then here, then here, then here, then here. So from left to right across the levels. Make sense? So always just basically in the standard order in the least surprising order you'd expect things to be added. So 8, 10. Now 10 is heavier than 8, so it stays put. Same with 50. 50 is heavier than 8, so it stays put. 20 is heavier than 10, so it stays put. 1 is pretty darn light, so it needs to bubble to the top. And the way bubbling works is that you just simply, the way everything knows whether it needs to bubble to the top is that it compares itself with its parent, right? So 1 asks 10, hey, who's lighter? Well, 1 is lighter than 10, so 1 swaps with 10, and then the process continues until it no longer needs to happen. 1 asks 8, hey, who is heavier? Or who is lighter? So 1 is lighter, so it bubbles to the top, and 8 sinks down. And only 1 really needs to compare because it's the only thing that was out of order. So it swapped, and then it swapped again, and now this is correct. Not only is 1 at the top, but each of the subheaps, like this guy, is also a valid min heap, right? That's the other key. It's a recursive property. So now, same deal with 4. We add 4 to the next possible position. 4 is lighter than 50, so we swap them. And then 4 is heavier than 1, so we stay put. The next item is 3. 3 is lighter than 4, so 3 swaps with 4. And then 3 is heavier than 1, so it stays put. All right, using the heap you drew above, draw the heap after removing an element twice. All right. Now notice, of course, that like this does not resemble at all like a tree, and like 50 is heavier, but it's on the left and right versus the right. That doesn't matter. All that matters is it a heap, and are the subheaps a heap? Is the smallest item smallest item always on the top in every context? So to remove a element from the heap, typically we're just removing the, in almost all cases, unless we're doing something really weird, we're going to be removing the root of the heap over here. Okay. So, and that's what we'd be doing on the exam anyway. So we'd be removing 1, but you can't have just an empty spot. Now, removal doesn't work by finding the next in order predecessor, right? Or next in order successor. The item that should obviously be there is 3 because it's the next smallest item. But how do we get there? Well, the answer is what we do is that we take the item in the back and we move it to the top of the heap. Yep, the item in the last position, and we move it to the front position. Now, obviously, because that's the easiest way to keep our complete structure, right? Because we got to keep the complete structure, the complete tree structure. But now that, you know, this is all, I believe the parlance is out of whack. So what we need to do is what we do is that we start looking at 4 and seeing if it needs to sink. Okay, because it is heavier. So 4 is lighter than 8, but heavier than 3. So 4 will sink and swap places with 3. So it's going in reverse, right? We're checking if the item needs to sink rather than whether or not it needs to float up. Similarly, 4 and 50. 4 is not as heavy as 50, so it can't sink any further. Okay, now if we remove twice, we're going to remove 3. I know 3 is like, but I just got here. All right, now 50 is over here. Now 50 is bigger than both 8 and 4. But you always swap with your smaller child because the smallest item needs to float to the top. So now 50. So 4 goes over here and 50 goes over here. Make sense? And if we remove 4, and if we were going to keep going, we would remove 10. We'd remove 4 and put 10 over here, and 10 would swap with 8. Right? So removing is a fairly straightforward process. All these operations take, just like trees, all these operations should take log of n time, each operation individually. Okay, Huffman coding, I'll skip. Okay, so now we get into the exciting bit, which is coding. Okay. So let's go ahead and new. Next. Practice exam 2. S 2022. All right, so let's see what I'll need. So really what I need is a node. That's pretty much it for this. Now that's all I need for just making sure that it compiles. But otherwise I'll probably need a, but otherwise I would probably need something else. Like if I need my full tree class, I can always put in my full tree class or use the index tree that I wrote, right? Okay, so but anyway, class exam 2. So I'm going to go ahead and make a node class very quickly. Public. Private. These are interclass. Private. Static. Class. Node. Which will take in some kind of E. And let's say extends comparable, just so that we have access to the comparable if we need it. That'll enforce that any E's that are made with no this work. And now we just need the local variable, and we don't even need a construct, and we just need a constructor. So let's create a let's see, not int E item, node E left, node E right, and then we just need constructor. And the way I only just do constructors that take in items. Some people write constructors that take in all the other stuff, but I like my nodes to basically start out as blank things that need to be attached. This dot item is equal to the item we pass in, and that is everything we need to get started. All right. Not too bad. Okay, so the first thing was size of tree, which was create a static method given the root of a tree or sub. Yeah, I made these static, doesn't really matter. But the point be, it just matters for testing purposes, but I made it static so that I could compile it easier. Public static size tree int size tree takes in a node E root or tree. They were interchangeable. right? Oh, and because I made put comparable here, I have to enforce that. Extends, comparable E. I mean, the other way I could do this, if I wanted to enforce comparables, which I don't always have to do, is I could just put, I could have make an actual tree class and make it an instance method, but honestly, that's just boilerplate stuff. It doesn't really matter. It doesn't really help me with your understanding. So here we're just looking for the root of a tree, and we're not going to be asking for that to return this dot size. We have to manually count the size of the tree, right? So the way we do that is, let's think of base cases. What's an easy thing to count? There's two cases for, well, we've got two nodes. So, sorry, we've got a node. There's two easy cases for this, right? It either exists or it doesn't exist, right? Or it doesn't exist and exists, rather, right? So if it doesn't exist, what size is it? What's the size of a tree that doesn't exist? 0, right? If root equals null, if it doesn't exist, that's a base case. Return 0, right? Super easy there. Okay. If the node does exist though, then basically it's 1, but also I can have children, and that's where it makes it complicated. And the size of a tree is equal to, well, however big the left side is plus the right side plus 1, right? We figure out how big the left size is. It's going to be so however big the left is, however big the right is, add those together, add 1 to that, because, and where does the 1 come from? It comes from me, of course. So I figure out, so the size of the tree is equal to myself, which is 1, plus the left side and the right side. Make sense to everybody? So with that, so int left size is equal to size of tree, root dot left, int right size is equal to size tree, root dot right. And finally, return left size plus 1 plus right size, right? Myself, my left side, myself, and the right size. Mind you, there's also nothing short stopping us from really making this really short by, instead of doing this, we just do, this instead, right? There's nothing stopping us from doing it in the return statement itself, other than it being harder to read, Does it make sense there? This one is easier than what you'd expect to see on the exam. Okay. Now, full is a bit trickier because you've got different cases, right? And there's one kind of undefined case here is the thing, right? So, all right. So a tree is full if it has no children, or if it has all of its children, or if it has 2 children. Well, actually, all the nodes in the tree, right, have to have 2 children, right? So let's put a pin in that and just think about the easy cases for a second, okay? Because that's what it comes down to, thinking about what is the easy stuff. Public, static, Boolean, E, extends, comparable E. I have to use autocomplete for Java. It's just such a long and is full, E node E root. All right. Just to quash it, I'm going to return true over here, but we'll remove that later. Okay. So first question, if root equals null, is that full? Well, all the nodes either have no children or have no children or 2 children. So I'm going to argue that it has that by being empty, it has no children and therefore is that way. And we need to check to make sure it's null so that we don't have a null pointer exception. Return true. But but we could basically now directly look at our children, and check the other base cases without having to do any recursion, right? We could, because if I have no children, then I'm a full tree, or a full subtree at least. And if I have only one child, then this tree, this subtree isn't full, and therefore anybody who called me is not a full tree. Make sense? So if root dot left equals null and root dot right equals null, ooh, we're good. Return true. And now let's go ahead and copy paste this a couple times. So if root dot left is, so here, I'm just going to copy paste because I know exactly what I'm doing. And it's warning me that I've got duplicate kind of cases going on over here. So thank you. So what I'm saying over here in the middle at line 41 is if I have a left node. So if I have a left node, but no right node, in other words, if I have one child, I'm not full, return false. And if I have a right node, but no left node, I have one child, so return false. Make sense to everybody? And technically these are mutually exclusive cases. So I'm going to go ahead and do an else if, and an else if over here, and an else if over here, so that I can do an else over here, okay, which is, and our else in this case is that I have 2 children, right? If I have 2 children, well then me personally, right, I'm full, me personally, I'm a full tree, but I have 2 subtrees, right? And I have no idea whether or not those trees are full or not. And and the whole tree is only full if those subtrees are also full. Make sense? So what we're going to do is that we're going to ask our subtrees if they're full or not. We can do that in one line. Return is full, root dot left, and is full, root dot right. If my left tree and my right tree are full, this will return true. If one of those are false, if one of them is not full, it'll return false. The whole tree will not be full. Make sense? So now, because we've got a return statement in every if condition, we didn't need that anymore. And thus our full code looks like this. So if it's null, then that's only going to happen if the entire tree is null, by the way. because in all other cases, it would fall under this. If root dot left and root dot right are both null, if I have no children, it's a full, then this subtree is full. If I have only one child, which is these two cases, then I can't be full, right? So return false. Otherwise, I have two children, so it's all dependent on my kids. No pressure, kids. Right? So now this one is comparable, I think, and tougher because we are dealing with two trees, which is we are checking is node A and are tree A and tree B equal, meaning do they possess the same data in the exact same way? What do I mean by that? So here's tree A and tree B. And they're the exact same, they store the exact same data in the exact same way. So they're equal to each other. Now, however, if I say, so here, these two nodes have different data, right? They have different data. Even though they have the same structure, it's different data, so obviously they're not the same. And finally, if they have a different structure, so here I'm going to draw 1, 2, 3. They have the same data, but now the trees are completely different, right? So these are not equal. So what do we need to do? Well, again, we're kind of limited in what we can look at without it getting really complicated, right? Really what we're asking is, here is tree A. I'm going to just denote it with an A. That root of a tree or subtree, right? It has some subtree underneath it, like this. And we have some subtree B over here. And these two subtrees could be massive. Figuring out, are these two things are equal is a hard thing. So don't try to figure it out. Try to figure out what you can, which is I've got two nodes. At the very least, I can check if these two nodes, if these two guys are the same, if A and B are the same, okay? And then I can make that their kid's problem, right? Because then what I'll do is I'll then compare I'll ask if A and B are equal, then I have to check the kids. So if A and B's left trees are equal, and A and B's right trees are equal, right? Which is their own question, but that sounds like a recursive case because that sounds complicated. If it sounds like it's tough, then it's a recursive case. If it sounds easy, it's a base case then. So let's work on a base case. So and I'm just doing, and I've made my test class differently than I made my exam class when I was writing this. So that's why I have to put in the E extends comparable E. It's not a big deal, it really isn't. Okay, the main thing is does the code is just making sure your code can compile, but honestly, I don't even, it's more important does the logical structure make sense, right? This is part of the reason that electronic exams take longer than paper exams when you're coding. It's because you're very tempted to have that thing compile and make sure that it compiles. Whereas I'm more interested, does the logic work? Okay. But it's got to compile, otherwise it's wrong, right? So that's kind of where you're going with. But honestly, it's again the logic I care about. But at the same time, like paper exams are much more difficult. I found that I really like electronic exams simply because it's a lot easier for me to read, like a lot easier for me to read. And also it's a lot quicker for me to grade. like a lot quicker. A lot quicker. Okay, so checking if these two trees are equal, okay? So return, I'm gonna just again quash it by saying return true. Okay, so first thing, like the questions that I have to ask myself is, do these nodes even exist? That's always a good question to start with. Do these nodes exist? And turns out we have 4 possibilities, not 2 possibilities, right? With one node, we had 2 possibilities, right? It either existed or it didn't exist, right? But for these guys, we have 4 possibilities, which are they both don't exist. One or the other, one exists but not the other, right? That's 2 of the cases. And then they both exist, right? So that's 4 cases. But 3 of these are really easy. So let's knock those cases out. Okay, case number 1, they both don't exist. If tree A is equal to null and tree B equals to null, then they're equal because they're both don't exist. And if they both don't exist, then they're the same, right? If they're both null, they're equal. Make sense? Right, and this actually kind of makes sense. Like if I'm comparing, you know, if I'm comparing these 2 trees to each other, where they both don't have a left child, and when I go to compare their left children, right, their left children are null, so that part would at least be the same. So if tree A is equal to null, so tree A is equal to null and tree B is equal to null, return false. They return true. They're the same. They're the same. Okay. However, now we're in the same case that we had for the other one, which is actually, I'm going to go ahead and put these since it makes it symmetrical. This is similar to what we were doing for the is full is what I mean, which is that if one exists, but not the other, return false, right? If A exists, but B doesn't, then they can't be equal. And if B exists, but A doesn't, they can't be equal. Make sense? And here it's it's warning me, wait a second, you can make that a plus statement else. Otherwise they both exist, right? It's the only possibility. They both exist. But we have one more base case that we can actually take care of. If they both exist, then we can check their data against each other, right? So else if tree A dot data, or rather tree A dot item, that's what I called it here, tree A dot item dot equals tree B dot item, and let's see, should I not this? I'm going to go ahead and not it, because if it's not true, then I can just return false, right? So if their items are not equal, tree B dot item, if their items are not equal, then those things are not equal because they don't represent the same data. Make sense? Now finally, else. Else, that means that both nodes exist and have same data. Right? That's where we are in this else, which means that now finally we're gonna these 2 root nodes. The 2 nodes that these 2 root nodes are the same. Make sense? So now the answer depends. Yeah, it is. Are my left node, are my left subtree the same, and are my right subtrees the same? If those subtrees are the same, then we're the same tree. Make sense? So again, that's just a one line recursion, which is if equals tree A dot left, tree B dot left, to check the left sides against each other, and equals tree B dot tree A dot right, tree A dot right, tree B dot right. And now what we can do, and now we can just simply remove this over there. And there's our code, which again is as follows. If they both don't exist, if I pass in nulls, then they're the same. Nothing is equal to nothing. Here we're asking if we've got something and nothing, or nothing and something, right? So as long as one of those exists, then and the other doesn't, we can just simply say, yeah, they're not equal because they don't have the same structure. And finally, if they don't have the same data, they both exist, they don't have the same data, return false. Both nodes exist and have the same data, turn tree to left, tree to right. Check if the left subtrees are equal, and check if the right subtrees are equal. Okay. Did I have one more for this one? No. Now we are on to this one, which is fairly straightforward. Write a method which returns what characters occur in a string and how many times each occurs. So I'm going to be verbose about this one, rather than using any clever tricks, just because I don't necessarily want to count on you remembering get or default in a high stress situation. For this one, we want to count the frequency at which all characters appear in this text, which I call word. So count the letter frequency. Okay. Okay, let's do this. Oops. Okay. So first thing we need to do is we're going to make we have to return a map. So I'm going to make the map of character to integer, right? Where the key is the character and the value is the number of times I've seen that character. Map is equal to new hash map of the same thing. Return the thing that I just made. Right, and now your code goes here. So now we have to count every single letter in. Now we have to count every single letter in the word. Now the issue with strings, of course, is that you can't use a for each loop over them regularly. You have to like make a for I loop, and then use car at to get the character, unless you know the trick, which is you write a for each loop for car C in word. But again, like I said, doing this natively doesn't work because strings themselves are not iterable. They don't have iterators because you can't move. And I think that's because in Java, you have to be able to remove stuff if you've got an iterator. You can't remove or something like that. But that can't be the case because what we're going to do is that we're going to turn it into an array, character array, which really is what a string is. It's just an array of characters. So this gets the underlying array. And what we're going to do now is that we can just simply now look at every character. And basically we're going to ask, is this the first time I've seen it or not? If map.contains key C, and I'm going to put a not in front of that. So if I've not seen this key before, then this is the first time I've seen it. So map.put C1. Else we need to get the number of times I've seen it before, which is imprev is equal to map dot get the number of times I've seen C before. And now we update that map dot put number of times C and the number of times I've seen it before, which is previous sightings, +1. Assuming I can type, which really has been difficult today. And now I can remove everything I need, or everything, all those other lines. So go through, if I've seen that character, put it into the map. If I have, if I haven't seen the character, put it into the map. If I have seen the character, get the number of times I've seen it and add 1 to that count and put that in. Right, because put will update that value. Okay. I'm going to skip this next one so that we can talk about analysis. Because this one is not going to appear on the exam. Okay. Categorization is not going to appear on the exam. I'm more interested in counting. So what are collisions and hash tables? And why do they occur and how are they handled? So anyone want to take a crack at any part of that? What is a collision in a hash table? Yep. So okay. So yeah, you have 2 points. So just to repeat for everybody, it's where you try to insert a value into a hash table, but you already have a value, but that key is already the index it wants to go to already has another key taking that location, right? So why does that happen? That happens because the space of the keys is infinite, but the amount of space we actually have on the computer is finite, right? So, right, what we do is that if we've got some key, we throw it into a hash function, which gives us an index that we can put that key in. But the hash function is going to sometimes have the same key for the same index for 2 different keys. Make sense? So we learned about 2 big strategies to handle them. How do we resolve collisions? What are the 2 big strategies? Open. Anyone? Open. Yes.
Open addressing.
Open addressing is one. And the other one? It has to do with, yes.
You put in a linked list at that index.
Yep, you put in a linked list at that index. So strategy 1 is open addressing. To briefly summarize that, but I will go into more detail. If open addressing simply says, hey, if I can't have my favorite space, then I'm just going to I'm going to take the next best space. Okay. The next available space that's open for me. And linked list and chaining or bucketing simply says, yeah, this entire idea of limiting ourselves to having only one key value pair in an index is silly. Let's put multiple values there instead. And so instead, in other words, it's a list. It's an array of linked lists. So the idea here is though that when you with a good enough hash function, all the lists are going to be around the same average length, and we enforce a limit on what that length is, some constant limit. So how does open addressing work? And the way open addressing works is that basically if I've got an index over here and I want to go into here, but it's already taken by some key, right? Then I'm going to look for the next available spot. But what the next available spot is depends on, and this is more detailed than I want you necessarily to go into if you got this on the exam, but I figured I'd be thorough. Right? If this spot is taken and I want to go into it, then what I'm going to do is I'll try to go into the next available spot. If I take a very literal meaning to what the next available spot is, so if I can't have index, then I'm going to have index plus 1. And if I can't have index plus 1, I'm going to have index plus 2. And if I can't have index plus 2, I'm going to have index plus 3. Right? That is called open addressing with linear probing, because we're trying to find the next available spot, the probing, and next is defined in a linear fashion. We are going up sequentially. Okay. Here's another way to do it, because the disadvantage with linear probing is that it can create clumps, right? And big gaps, because if a bunch of things collide at the same point because we're unlucky. The other solution is if I can't have index, then I'm going to have index plus 1 squared. And if I can't have index plus 1 squared, I'll have index plus 2 squared. And if I can't have index plus 2 squared, I'll have index plus 3 squared. And if not 3 squared, I'll have 4 squared. This is called quadratic probing because that's squared. This creates less clumping because everything is more spread out. But from an efficiency standpoint, this is slightly less efficient in terms of calculation because we just simply had an addition operation before. And now we have an index plus offset times offset. Right? We have a multiplication operation plus and an addition operation in there. So it's slightly less efficient. That's the disadvantage here. Now, why do both of those linear probing work? Well, the idea here between hash tables, again, is that hash tables have a finite amount of space. But if we keep enough space open, then if everything's evenly distributed, then we can find things in constant time. Okay. Similar to the analogy I've used a lot is parking decks, right? It takes a lot of time to find, if the parking deck is got only one space in it, it takes forever to find that empty space, right? Like somewhere in the top, and like turns out that somebody's like already half parked in it, so like, it's like really tight. It stinks. Okay. So, and then the other, but if the parking deck is half full, or half empty in this case, half empty is a good thing, right? Then it takes like no time at all to find a parking space, right? Or maybe all those things on the bottom floor are taken, but you've got plenty of choice on the other floors. You know, nice and away from people, nobody's going to dent your doors and stuff like that. You know, the point being is that finding open, so having plenty of open space speeds this up. All right. What is the worst case runtime for insertion and deletion algorithms in a binary search tree, and why? Okay. So what are the worst case runtime? So what is the average case runtime for binary search trees on average? It is log n. It is log n. So on average, every operation in a tree is log n, because basically on average, in most cases, right, you've got half the tree on the left, half the tree on the right. So by going left or right, you removed half your search space, right? So basically think back to binary search, where basically every time we did an operation, we cut the search space down in half, and trees basically live on that. They're not always, they don't have the constant time operation of hash tables, but log n for everything is pretty darn good. Except that that's the average case. What is the worst case for a binary search tree? The worst case runtime is O of n. In an unrealistic example, it's just a linked list with extra steps. Like this. Right? Completely unbalanced. Because that's the key. It's log n if it's balanced or close to balanced. If it's an unbalanced tree, not then no. So what does an unbalanced tree look like? Well, to show you, we're going to use a very simple English sentence that you've all heard before. The quick brown fox jumps over the lazy dog. So the is the root. Quick comes before QRST, right? Quick. And now brown comes before all those. Fox comes before T, comes before Q, comes after this. So fox jumps. You can see where this is going. Jumps over OPQ over the quick brown fox jumps over the, we already have the, and now lazy would go over here, and then dog would go over here, right? It's completely unbalanced. Another easy example of an unbalanced tree is, again, alphabetically, the taking your hand across the home around on the home key and just dragging it across. A, S, D, F, G, H, J, K, L. A, S, D, F, G, H, J, K, L. Right, and notice that each step of the way, we're not knocking out half of the tree. We're knocking out a single item, right? It's just a link. It's just a linked list of extra steps at that point. Okay. So that is why, because if it's unbalanced, you get bad runtimes. Now, chapter 9 in the textbook, which we don't have time to go over, is all about balancing, is all about self-balancing binary search trees. And the way self-balancing binary search trees work is that they use these operations called rotations. Basically look like this. They're basically the relative levels of stuff changes, where the yellow node comes down and the green node comes out up. And notice how the beta over here, because they love using their green, goes from being the green's left node, so the green's left node, to being yellow's right node. Or in terms of animation, you have something called the root, you have the pivot, the root moves down and the pivot goes up. And the idea here is that this doesn't change, this changes the tree structure, but it can adjust the balance of a tree. Now, all like a linked list, all that's moving is the pointers. So this is a constant time operation to do a rotation. And it turns out that if your tree was balanced, okay, there's your condition. If the tree was balanced in the first place, okay, and now adding or removing an item made it unbalanced, then it just takes log n steps to fix that using rotations. Okay, and that just depends on your kind of tree you're building, because there's different types of balanced trees. However, that's not the only way we can do these trees. There are 2-3 trees where nodes can have both a 2 node, which is a standard node, and a 3 node, where you have 2 values in the list, so in the tree, and everything less goes to on the left, everything bigger than A is less than B, everything less than A goes to the left, everything bigger than B goes on the right, and everything between A and B goes in the middle tree. And that's and why do they do that? Because you can self-balance that. It has different ways to add items into nodes, and then if it becomes too big, you split it. If you've got balancing, you've got AVL trees, which is named after its inventors, which keeps track of how balanced it is. And then, right, and then it has a bunch of code for what to do for a operation, for rebalancing. B tree, another variation that's popular for school is the red-black tree, where worst case scenario is log n. And the idea here is you cover some nodes red and some nodes black with all the null pointers being considered black. And the idea here is that let's see, what was it? I believe that all the routes have to a leaf, to a null, have to have the same number of black nodes. Yeah, that's it. So if you can see over here, getting to a nil has this, all nils have the same number of black nodes, and that's how it keeps it balanced. So 13, 11, null. So that's 3. 13, 25, null. And then it has very specific rules as about how you add. It's similar to what's called a B tree, which have a variable number of child nodes. So there's different kinds of ways of doing this. So trees are very important though, because you use them for files and stuff. And let's see, tree data structures. You've got B, B plus, B star. Let's see, B plus, the B plus tree, very popular for data stuff. Razor, FS, NFS, NSS, JFS, BFS file systems also all use this type of data for tree indexing. NTFS, which is the Windows file system, uses B plus trees for directory and security related meta indexing. X4 uses extent tree, a modified B plus tree for file extent indexing. And X4, by the way, that's Linux. APFS, let me guess, that's Apple. Apple file system uses that kind of uses B tree. It's basically using a B tree. NTFS B tree variant. So pretty much everything is a variant of the B tree at this point. So you know, trees are important for file structures, but really you only need to get into the nitty gritty of them if you're really, really, really interested in file structures, that kind of stuff. And honestly, that you only do that if you're actually really interested. So